Hello, my name is Jeff Salzman, and at the recent Vintage Computer Festival East 2023, I gave two classes on assembly language program on the Commodore 64. Now, I was only given 2 hours, well, 1 hour per class, and the classes were repeated in subsequent days, to try to instruct people on how to get involved or what they have to think about when it comes to assembly language program on the Commodore 64. The first class was entirely theory based. I explained basically the 6502, or primarily the 6510 microprocessor, the way it's organized, the way it's laid out, all the registers and other features it has, like a stack pointer and program counter and status registers, along with the different types of addressing modes. That is a lot of information to give out in 1 hour's time. So my next class, I decided to go without any kind of prepared presentation and just with the classroom and using a Commodore 64 emulator. They were all sitting in front of actual Commodore 64s following along. We basically went through and just did some sample programming. Nothing big, nothing heavy, nothing tweaked for speed or technique, just to show how Commodore 64s can be programmed in assembly. Some of the questions from the class were, do you have any more information on this? Or is there anything else we can learn? Are you going to do this class next year? They're basically questions that have yes as an answer. So I decided to put together this video as an after-class self-paced practice. I will be the first to say I'm not the end-all be-all of assembly language programming on the Commodore 64. I will teach it the way I know it. I'll teach it the way I learn it. I know assembly language can be tough for some people to grasp the concept. And I was that way myself, and I still am to some things. Even when it comes down to some of the addressing modes, like indexed, indirect, and indirect indexed and all that, it can get confusing. So this video, which may become a video series depending on popularity, is designed to slow down the pace a bit, go into detail about what's going on. I'm not going to present the theory like I did before. I'm going to present the actual coding, and then I'll explain bits about the coding as I go along. Now, I am recording this in a not so professional studio using OBS Studio software, which is great, by the way. It's very useful for putting together multiple screens that you can switch between, and it just records everything in the background. There will be noise in the house here. You may even hear the dogs bark. So if you hear the dogs barking because they saw some fly flying across the window, I will cut the video and come back in when it quiets down. This is not going to be a professional recording. It's just going to be basically one-on-one, myself to you, whoever is watching the video and is interested in programming the Commodore 64 in assembly language. I'll do it my way with the tools that I like to use. And I hope you enjoy it. And as always with any of my YouTube videos in the Vintage Volts world, if you have any questions, send it to me directly. You can go to my website, www.vintagevolts.com, or you can post in the comments below. Getting started, I'm going to use the WinVice emulator for Commodore 64 environment. You should be able to see it right here, and I will load up the assembly language software that I want to use, and let's do a load. We get right into it. I'll load the directory of the disk so you can see what it is. For those who attended the class, you already know what it is. For those who are watching this for the first time, I've actually, there are probably better assemblers out there, and there's probably worse assemblers. I just grown accustomed to this one personally over the past 5 or 10 years, and I'm going to stick with it for this, if not to demonstrate an alternate way that one could quickly program in assembly language. And when I list this program, you'll see that it's called, well, let me list it again because I was a little too fast. It's called PAL Assembler by Brad Templeton. PAL Assembler is a personal assembly language assembler, if I recall correctly. It's an interesting assembler where most assemblers, or at least the ones that I've seen so far, and I really don't know of all the ones out there. I know there's at least 20 plus that are available over the years the Commodore 64 has been in existence. But this one works in a very unique way. And there may be others, one or two, that do the same thing. But where most other assemblers expect you to load their program and you'll have a full screen interactive, kind of like a scratch pad or notepad editor, this one works within the basic environment, meaning that it runs as a stay resident program, and as you write your assembler code, you have to do it with line numbers as you do with basic. That seems weird at first, but it does. If you're quickly testing out stuff or want to write up something quick, it does have its benefits, because you're really not having to jump out of your development environment to test some applications. And I'm using a D64 file that's available out there. I will provide links in the notes down below this video. This one is called PAL Power D64. So I already have it installed or loaded up on here. So I'm just going to go ahead and load the PAL program. And I really didn't do anything to speed up disk access here. In this emulator, it's going to load, I believe, as fast as it normally would load off of a disk, which could take a little while, but if you want the real Commodore 64 experience, here you go. I think it takes about 15 or 20 seconds to load, and when it does load, we can look at it. It's a simple, you may have seen these types of machine language programs before, where it has a basic header that when you run it, it runs the machine language portion. So when I hit run here, it just gives me some text. It says, PAL copyright 1979. It's funny, the copyright is before the Commodore 64 came out. It's because this assembler actually came out before the VIC-20. It came out when the PET came out, and it was in it. The story is this assembler came into the public eye because it was written specifically to create another type of program, and I forget offhand which program that was. But it has been around for a while, even before the Commodore 64. It just has been rewritten for the Commodore 64. And other items that you see on here is basically templates of what happens when we compile actual applications. We run compile actual assembly language software. This number here would come up when we compile. It indicates the 2-pass compiler, and this shows the range of addresses in hexadecimal from start to finish. And you'll see how that works. Right now it says 0 to 0s because it really didn't compile anything. It just ran, and this is the status message. So how does PAL work? Well, PAL, you actually launch PAL by calling a machine language call to memory location 700. That's where it's residing, or at least that's where the vector to the PAL assembler is residing. So in order to compile anything, you have to do an SYS 700. I'm just going to put a few blank lines in here for clarity. And let's just start with a simple little program here. It's a program that is included with the PAL assembler's instructions, and I'm actually going to go by memory for this, and I might make a few modifications on the way, but this is to demonstrate how to use the PAL assembly language or assembler to get started. You need to have a few lines of code to set up the environment. So everything has to start with a basic line number. So just like we were writing a basic program, line 10, very first thing that should be in your basic program here is the sys700 call. And generally you would follow it with a list of compiler options. In this case, the option I want to use, since I'm just writing small code and I want to run it directly from memory, is I want it to print out the lines it's compiling as it's compiling so I can see it going. And I want to create my output, this is an O, not a 0, to an object file which is going to be stored in memory. And really starting the code, you need to have, for those who've worked with assemblers before, you have to set your program counter, basically the start of your program. That's indicated by using the asterisk followed by an equal sign and where in memory you want things to start. So in this case, I'm going to start it at this location in memory, which in decimal value is 49152. That's the simplest header. And now I'm going to start writing some code. This code is going to do something really simple. It's just going to take whatever contents are in the first 256 bytes of RAM and output it to the screen. It'll just put it in screen memory. Whatever the value is in each of those first 256 bytes, it's going to represent a screen character, a screen printable character. It's just going to put that out there. We're going to see garbage characters, but this just shows how you would write a simple assembly language program that performs some function. And as I told the people in the class, that because of the very few registers that the 6510 has built into it or has access to directly, a lot of thinking on assembly language program is simply keep in mind that you're moving values from one point to another, one point to another, one point to another. And we typically do that by loading a value from one location, one specific value, and then we put it somewhere. And we just keep doing that. If we have to do it in loops, if we have to just write a long series of things that, code that performs that function, that's really what's going on. That's how you program this CPU, this microprocessor, is you just make it move stuff from one place to another, and variance on that. So let's start line 40 with our code. First thing we want to do is establish what we need to create a loop. We want to count 256 items, or basically we have to count 0 through 255. Most numbers, most starting points in a computer like this doesn't go from, even though it's 256 items, it doesn't count from 1 to 256, it counts from 0 to 255. Same number of items, just 0 based. So one of the registers that you can use in the 6510 is called the X register, and it's really good register to use if you want to keep track of counts. There's also a Y register that can do the same thing. They actually have certain capabilities when it comes to selecting new addresses when you're moving data from one location to another, but we're going to use X. It's just very common practice. So every 6510 opcode or command is a mnemonic that's made out of 3 letters, and the 3 letters generally defines, if you look at it, kind of defines what the opcode does. So we'll start with, we're going to load the X register with the value. We want to start at 0 and we want to count up. So we can load the X register with a 0. Now I'll be making intentional and unintentional mistakes with this, so just bear with me. So, loading X with a value, a specific value, we have to precede that value Remember when I said the dogs will interrupt? Well, I didn't even think about the phone interrupting, so had to take care of that real quick. And continue on here. To load a register with an explicit value, we have to precede that value with a pound sign, or in today's vernacular, a hash symbol. And I want to load the X register with the value 0. And it's that simple. So load the X register, and this means immediately. It's what's called immediate addressing. So we want to load the X register immediately with the value 0. Now, in most assembler programs, you can represent a decimal number with just the number. Like if I wanted to load this with the number 147, I can do that. If you want to load it with a hexadecimal value, you have to precede that value with a $sign. So hexadecimal, I think 147, I believe, is 93. So hexadecimal 93 is the same as decimal 147. You can also use binary numbers with just the zeros and ones by preceding them with a % sign. And then you just put your series of bits in there. I don't know what that converts to off the top of my head. I just put them in there for visual, but it's common practice to think hexadecimal and do hexadecimals, so I can do this. I can also do this too, because when you're working with the numbers 0 through 255, it's generally 2 hexadecimal places, and this just kind of fits right. And I'm going to leave it like this, but you can also do this if you just want to be, quick and dirty with it. But I'm going to try to conform to a convention and just write my command this way. So load X with the value 0. Next thing I want to do is, so this X register is going to keep track of the count. And now that I have a count, which incidentally starts at 0 right now, I need to do something per count. So I'm going to create a loop. And in PAL, you can create a loop. Let me just show you how each line can break down. You can have an optional label, and I could call this label, I can label this loop. So and then the label's optional. Like on this line up here, if I inserted text in front of it, that text would be the label. Here, I can start out loop, and then I can put in the code for my next opcode. Here, in this case, I want to load the accumulator. The accumulator is probably the busiest register in a 6510 microprocessor. Excuse me. This is the one that you'll bring values in from another location and put values out to another location. This is going to be the workhorse register, and it's always going to be used. You bring something into it, you put it out somewhere, then you bring something new into it, put that out somewhere. So I have a label, I have an opcode, and then I have the operand, which is the value you put beside the opcode, like I did up here with LDX. This is the operand. I want to load X, and this defines what I want to load into it. For this, I want to load something from memory. So this is a new type of addressing mode. It's called 0-page addressing, which means I need to specify the 2-digit hexadecimal location for the first, what they call page of memory. Each page is 256 bytes long. First page, or page 0, which is technically the first page, starts at memory location 0 and ends with memory location 255. So my operand for loading the accumulator is I want to load from register 0. RAM location 0. So that's my operand, but I can't really do this the whole time in a loop. It'll keep loading the same thing from the same memory location. So we will index this with, the X register. What this means is It'll load the accumulator with whatever it sees in memory location 0, but it'll add the value of the X register to memory location 0 to get the new memory location it needs to actually look into to grab the value. There's another way of doing, like if you're not doing anything in page 0 or using the 0 page stuff, this can actually be represented like this, which is considered absolute mode. That means you're absolutely telling it to go to this specific memory address. And then in this case, we can stop here. We can just say load accumulator from the contents of memory location 0000. And that's it. It'll look right there and get it. But we don't want it to do that. We want it to start with that point and then add whatever is in X. And that new calculated value is the memory location we want it to go to pick something up. So this line will work, but since we're working with 0 page, we can do that, and the benefit for it is we can use one less clock cycle, 1 millisecond faster speed, because it's 1 millisecond faster for the microprocessor to look at page 0 than it is to look at any other page of memory through all 65,536 locations of RAM. Plus, if this is a really big file, a source code file, the more you can leverage 0 page or any of these little shortcuts, the less you'll save, or the more memory you'll save storing your source code on disk or in memory before you compile it. So that's a lot of talk, but as you work with assembly language and as we continue on with this, you'll understand what it's all about. There's a lot of different ways of doing things in assembly language on any microprocessor. There's just some little tricks and tips here that I'm just going to show you right away as I do them. So we have, like I said before, we have 4 parts that we can put on a line in this assembler. We can put a label, we can put our opcode, we can put our operand, which covers all this, and then if we want to, we can use a semicolon, and we can just put a comment here. It doesn't have to be anything, but you can put this. The comment's optional. If you put it there, just make sure you put the semicolon in front of it. That way the compiler doesn't think you're trying to issue an instruction. So these are the 4 parts. However, you might see how it could be a little difficult to read this. And actually, I'm going to do something here. Got to make sure you hit enter after every line. This isn't a free-form editor. That's the only drawback to working in the basic environment, is that you have to hit enter after every line, or it will not put that line into memory. So if I do a list right now, okay, you see I have all that there. But when I go back and change it, I want to do something here. I want to go ahead and I want to change this line. I'm going to make loop equal to asterisk. Now, why would I do that? I think it makes the code a little easier to read, because on line 50 we're basically telling the compiler that I want to start my loop label right where the program counter is right now. Because when it compiles this, it starts the program counter at this address, but as it builds it, the program counter goes up internally. And then when it gets to this line, it says, okay, I'm going to mark this point, whatever the program counter is, I'm going to mark this point and call it loop. That allows me to better structure my code so I can see where the loop starts, instead of trying to find the beginning of a longer line that has the word loop in it. Because elsewhere in this program, we're going to tell it to go back to wherever loop is and repeat the same instructions between the loop and the point where we tell it to repeat. So we're starting the loop here. Then I will put in that line I had before. Load the accumulator from memory page 0, location 0, indexed with whatever values in X. And now we got to put this somewhere. Line 70, we're now going to store the accumulator's value to a new location, which just happens to be 0400. And that's the absolute addressing I was telling you about. we're specifically telling it we want to store whatever's in the accumulator register directly to 0400 memory location. And again, we're going to index it with X. We're going to expand upon that. So 0400 plus the value of X, whatever that adds to, that's memory location to actually put the value that's in the accumulator back into memory again. So basically we're taking something from one location, indexed by whatever X is, and storing it in another location, which just happens to represent all the memory cells that hold the contents of the screen. So we do that once right here, so we want to do it again. But in order to do it again, we need to increase our counter. So I hit 80, or type in 80 and do INX. That's all you need there. It means increase the value of the X register by 1, always by 1. If you wanted to increase it by 2, you would do INX again. You would actually run it twice and it'll increase it by 2. So we've increased the X register, so after the first loop, or first run through the loop, we now increase the X register. It'll go from 0 to 1. And now we need to see, did we count 256 off? Well, here's a little trick. It's something you need to think about when thinking about the 6510 CPU. Any action you do, whether you're loading a value or storing a value or increasing something, it's going to create a system state in the, it's going to create a status in the 6510. And one of the statuses is, did that action create a 0 value? So logically, when we did the LDX up here and loaded it with a 0, well, that created the 0 value. We actually explicitly created a 0 value. So that particular status at that moment in time was a 0 value. When we do this INX, we created a value of 1. It doesn't make any difference how you create it, it's just that happened. So we had created a value of 1. Doesn't make any difference if it was in the Y register, X register, the accumulator. We created a value of 1, which means it's not 0. So we're going to check against that. So if we'll do an opcode called branch if not equal. Not equal to what? Not equal to 0. So we increased X by 1. That means we do not have a 0 state. So we're going to have to branch somewhere. And in this case, we're going to branch to what we labeled loop. The compiler is going to see this loop and assign a memory location for it. And when it compiles this line, this line, this line, and starts to compile this line and realizes, okay, it's going to have to create a branch to loop, it will substitute the word loop with the actual memory location where this command starts. And that creates our loop. So until it reaches a 0 state, it's going to keep running these 3 commands over and over again, looping through them. And what creates the 0 state when we keep increasing X? It's because this is an 8-bit machine and the registers are only 8 bits. So when you count up, starting at 0, count up 1, 2, 3, etc., it goes to 255, and then the next increase will roll it over to 0 again. That creates the 0 state. At that point there, the line after this branch if not equal, it continues executing after this point. So we want this to do something. And I'm just going to be short and quick, or quick and dirty on this one. So after, it'll keep looping until X reaches and rolls over to 0 again. And then after it's done with that, it means that this branch will not be satisfied, and it's just going to drop through to the next one, or be any. This branch, yeah, will not be satisfied, so it'll go to the next one. And here we're just going to put in the opcode RTS. And what that means is it'll stop. RTS means return from subroutine, and you can put that at the end of your assembly code that you initially run. So to break down what's going on here, we'll go back to the top. Line 10, we launch the PAL assembler. Line 20, we have the options we want. We want to see our output as it's compiling, and then we want it to compile as output it as an actual object in memory, which just happens to start at this address in hexadecimal. And we just want to do something simple. We want to start counting at 0, and we're creating this loop here. You know, we're just marking this as a spot we want it to go back to. So we created this label here, and then we'll just do load from memory address 0 plus the value of x, whatever happens to be in there, and we store in memory location 0400 plus the value of x, and then whatever's in that calculated address, increase x, and as long as it hasn't rolled around to 0 again, we're going to keep looping. And then once it does hit 0, it'll continue on and stop here. So making sure that I hit enter after everything. This is the program. Nothing very big, just some stuff that had to be set up beforehand. Now this is where the uniqueness of the PAL assembler works. In order for me to compile this, all I got to do is run it as a basic program. Because the first line it'll see is it'll do sys 700 and start executing the assembler code. From that point on, PAL takes over and looks at the rest of your program as if it were assembly language and actually does the compiling. So I'll run this, and I'm going to cross my fingers no mistakes come up. And by the looks of it, none did, because if there were mistakes, you would see lines with 3 asterisks at the beginning, might say something like syntax error or whatever, that tells you, it always puts that before the line it had a problem with, so you can go back and see which line it was. But here it compiled. It converted everything to the opcode and values that it needed. Here it assigned loop as location C002, which actually decodes a certain way. I'm not really going to go into branching so much here, because you really don't need to know the intimate details of how branching works unless you really want to code things manually, and I don't recommend that. So here's where the branch occurs, but see, even though loop's assigned to C002, it didn't put anything even closely related to C002 where it goes to. What it did is it put in a value which represents a certain number of memory locations backwards in memory. So it's like an offset. But the compiler takes care of that for you, but this is really what's going on in the background. And then there's the code to stop. So our whole program fits between C000 and C00B, which is basically 12 bytes if you include the 0. So it's compiled. Now for me to run it, I don't run again. If I run again, it'll recompile the program. I do an SYS 49152, which is the decimal equivalent of C000. And you see at the top of the screen there, a whole bunch of garbage. That's basically a representation of what came out of the first 256 bytes of memory, and whatever that value is translated into whatever character would appear if you put the exact same value in screen memory. Quick and dirty, gives you an idea of how you're going to program an assembly language. This should start giving you a fundamental or a foundation of what to do as you continue. You may notice though that this is being quick and dirty like this. We could try to make it a little neater. You know, I'll list this. You can see here that we can change things. The question becomes, how do we change it? Or what's the best way of changing it? For me, I'd rather just maybe clear the screen. And there's different ways you can clear the screen on the Commodore 64. If you're not familiar with some of the nature of Commodore 64 text codes, called PETSCI, you can actually print certain key functions on the Commodore 64. For example, you can actually print a cursor up and it will perform a cursor up. You can print a home and it will move the cursor to the upper left hand corner of the screen. Well, there's also a clear key, or clear, shift home, and that will clear the screen. But you can also print it with in code, whether it's in BASIC or assembly, just by running whatever routine or whatever code it takes to print a value. In BASIC, you would use the print command, and when you open up the quote and hit shift clear, it puts a funny special character in there that lets you know that this is where you want it to print a clear screen, and then you close the quotes. In assembly language, we don't do that. We can't print special characters within quotes in that sense. But the Commodore 64 does have what's called a kernel, which is a series of built-in routines that the programmer can use for themselves, and it's very conducive to assembly language stuff. Let me show you here. I have a copy of the book loaded up here. It's called the Commodore 64 Programmer's Reference Guide. It is in my opinion, the best book you can buy if you want to work with, study, manipulate, understand the inner workings of a Commodore 64. In this book of 504 pages, you can see there's a lot of information here. Quite a bit, and I'm going to scroll through here quickly. I'll be bouncing back and forth as I try to remember which page the information I'm about to talk about. Well, hey, let me stop here real quick. Okay, these are 6510 microprocessor opcodes. You saw the one for BNE, branch on result not zero. And we did LDX, load index X, with memory. And memory is just a soft definition. It could be the contents of memory memory location we specify, or specify with an index, or it could be an immediate value. That's also considered memory. But they use the term memory for that. So this book shows you all the different opcodes that are available to you, and what they mean, and how they work, and also the details. Like you see, this number says opcode 0, or opcode, I'm sorry, 70. It'll be a lot clearer if you look at the document directly, and I'll put a link to this. This is on archive.org. I'll put a direct link to this in the notes below too, so you can look it up for yourself. But if you're really into working with the Commodore 64, I recommend finding one of these on eBay or whatever. I don't think they're very expensive, but they are very useful in print. But as I go through all these, finding the next page, forgot, just wasting time here. I'm trying to get to the kernel. Here we go, the kernel. The kernel is a set of routines that primarily for machine language programmers, because there's certain things that BASIC will do for you implicitly that it's just hard to do unless you have routines for it. You could write your own routine to put things on the screen, but why reinvent the wheel? So the kernel has a lot of these, what they call user callable kernel routines. Like now the names are just for reference. I don't think you can reference the name in the assembler. I actually never tried, but you do have to reference the hexadecimal address where they start in order to launch them. Here's one, output character to channel. It's called CHR out. This is the one I'm actually referring to. So I'm going to go to the page for CHR out. And it says here, the purpose is to output a character. So this routine outputs a character to an already open channel. Now by default, the screen is the open channel. unless you tell this otherwise, and I'm not going to get into that. We're going to assume it's just going to go right to the screen. So it'd be like we can give it a value or give it a character and it'll put on the screen. It'll print it to the screen for us. And then we give it another character, it'll print it on the screen beside it, as if we were typing it. We can just keep feeding this thing individual characters and keep calling it, and it will put it on the screen as if it was typed. So we want to type the clear key like we can do in BASIC and then output it as a character, and it will clear the screen for us. So basically this says you have to load the accumulator with the value that you want to output, and then you call this routine. It's actually very simple. So I want to go elsewhere in this book. Again, as I try to find it, it's one of the appendix pages. I really should bookmark this. There is that much information here. Here we go. ASCII and character codes. And this might be a little tough to read on this screen, but there is clear home. It's decimal value 19, and I can use that value if I want to. I can mix decimal and hex numbers, but if I wanted to do it, this would be F. This would be 10, 11, 12, 13. It would also be hexadecimal 13, but this represents the clear home key. And let's see here. Actually, the shifted version is 147. The way this table works is the first 128 characters is if you don't hold the shift key. The second 128 characters is as if you're holding the shift key. So I need to do a shift clear home, which is decimal value 147. And I'm not going to bother doing the hexadecimal conversion. We're just going to use that value. So I see here that I need to use I need to send the character 147 out to the screen. And what I should have got while I was back here is the location for that kernel call. Here we go, character out, FFD2. Okay, so switching back, I need to modify my program here to output the character 147 and then send it to FFD2. Now this is one of the drawbacks to a basic layout or the PAL assembler using the basic environment, is we can't just go up and insert a line, but we can insert line numbers. So we got to figure out where we want to put this. We want it to clear the screen before it does anything. So logically we should put it anywhere between 30 and 40. And that's what I'll do. And I can do it down here just easy. I just do like line 33. This is the reason why even in BASIC we leave gaps of 10 lines for our line numbers, so we can go back and insert something a little bit later. So we need to load the accumulator according to the instructions for that with an immediate value of the code we want to send, in this case 147. So that's all that line is. And then to call the routine at FFD2, I'll just do line 36, still keeps it in there. We would use what's called a jump to subroutine. And then we put the address in memory where that subroutine starts, in this case FFD2. Make sure to hit enter after everything. So now when we list this, we added 2 additional lines in our code. So the first thing it'll do is it'll load the accumulator. See how busy that accumulator is getting now? We load the accumulator with this value, and then this routine expects to see a value in the accumulator, and it will do what it needs to do to type it out to the screen. Then it'll start here, starting X at 0 and counting up and loading stuff from memory, putting out. So basically what this will do is it'll clear the screen, put our cursor at the upper left hand corner, and then do its job. All we really need is to clear the screen. We don't care where the cursor is at, because we are explicitly telling it to start at 0400. We are explicitly telling it to start putting stuff out at the upper left hand corner of the screen. So now that we changed this code, we need to rerun it to compile it again. And as you can see, it's getting a little longer. It's not C00B now, it's C010. I added a few extra bytes. Now that it's compiled, we can run by using the sys command to launch it at its compiled location, and now it clears the screen first. But look at that. We get the word ready in here, because the cursor was technically sitting at the upper left hand corner here, and when the machine language program got done, BASIC took over again and it put the ready here. So we don't want it to do that. We want to see our fancy work here before we exit the program. So we'll put an additional code that will watch for a key press. And to do that, we'll once again make reference to the kernel calls. Notice I didn't have to shut down the computer, the Commodore 64, like some assembler programs. Well, these are small enough programs, so it won't be a problem, but I didn't have to shut down. I'm still in the basic environment. If I do list, there's my program. But we want to add more lines, so I'm going to go back to this book here and find a kernel call that we can use that will help us just watch for a key to be pressed. And this one called get in at FFE4 says get character from keyboard queue, or the keyboard buffer. Commodore computers have a 10 key keyboard buffer, so if you type faster than it can work, it'll buffer up to 10 keys. But when a program is running and not accepting keyboard input, you can press a letter and it will queue up in that buffer. We're going to take advantage of that. I think these are listed in alphabetical order, so I already went past it. So here's get in, get a character. So it says if the channel is the keyboard, and by default inputs is the default input channel is keyboard. When it says these channels, a disk drive could be a channel. You can have a channel in from a disk drive, out from a disk drive, in from tape, out from tape, in from disk drive, out to printer. Each of those is a different channel. Input from the expansion port or the user port on the back. Those are all channels, but unless you specifically go and change those, the environment's already set up that the input would be a keyboard. So it says here, in order to use it, and I'm just skimming through this now, is you call this routine and then you check the accumulator register to get the character value. If you don't press a key, the character value is 0. So what we want to do here is we want to call this routine, then check the value of the accumulator to see if it contains something other than a 0. Going back to the emulator again. So where would be a good point to do this? We want this program to do its job and then wait on us. So we might as well just start at line 100, and we can overwrite this RTS and put it in later. So line 100, the loop is done. It's now going to go to whatever we put here on line 100. So we need to have a label. We need to put a label here, because after we get that, after we call that kernel call, then if it doesn't match our requirement, we need to loop back and keep doing it until it does. So I'm going to set a label here, and I'm actually not good with labels, creating good labels. You can't use labels that are the same as a mnemonic, and I don't think you can use labels that are the same as a basic keyword. So I'm just going to, I'll just call it wait loop. So I'll set wait loop now to whatever the program counter is here right now. So when I want to keep running this loop, I'll just branch to wait loop. Alright, first thing I want to do is call the get in kernel function, and that was FFE4. So I would do a jump to subroutine FFE4. Now when that runs, the accumulator will hold whatever key value was pressed. what you will have to realize is we don't have to do anything specifically with the accumulator. I mean, the accumulator has a value. If we needed to store that value somewhere in memory, we can do an STA, or if we have to do what most functions, like whether it's addition, subtraction, unless it's a specific function for the X or Y register, it's always going to affect the accumulator. But that's not what we're looking for here. We know from earlier when I told you about the BNE, branch not equal to 0. If we bring any value in, if a keyboard thing is pressed, a value other than 0 appears in the accumulator. Well, that will create a non-zero state. But if nothing's pressed, it returns a 0, which will create a 0 state. So we can check if we don't even have to look at the accumulator. We just need to check to see if the state became a 0. And then we could just branch based on that. So line 110, we're going to do branch if equal to 0, because a 0 state exists. Because the accumulator got loaded with a 0, that creates a 0 state. We're just going to branch to the wait loop. And that's basically it. It'll just keep looping this until we create a non-zero state by hitting the key and putting a value other than 0 in the accumulator when it reads the keyboard. So 120 RTS, the end of our program. I'm just going to list it again to make sure I hit return after every line, because if I didn't hit return after a line, that line would be missing or altered. So I'll run this to compile it. Oh, look at that undefined statement. What does that mean? It says it's before BEQ wait loop. Did I spell something wrong? Like I said, I'll make some. You know what? I did not hit enter on my wait loop. So I made a mistake there. Okay, I need to put my wait loop in before line 100. And you guys may have caught this by now. That's fine. I'm leaving it in the video. I don't care. You know, everybody makes mistakes. So I need to put my wait loop in. So 95, I'll do wait loop equals current program counter. Now I hit list. There. Now wait loop is defined. Now when it compiles, it knows where to go when it compiles this line. Let's try this again. No error this time. And notice our program is getting progressively longer. This number is getting higher. Now if I do a sys49152, remember, run your program to compile it first in this environment, and then do a sys49152 in this particular case. And there it is. It's hanging there until I hit a key, because we don't see that word ready on the second line, but when I hit a key, there's the ready. But it still kind of looks stupid, doesn't it? Let's just make it clear the screen when it's done. How about that? Gotta love this full interactive screen editor, right? Because I can just move the cursor down and do stuff, and there it is. So what can we do here? Okay, I can just repeat what I did in the earlier lines. I can just do LDA 147 and JSR FFD2 as my last lines. 120 LDA 147. I'll make sure I hit enter this time. And 130 JSR FFD2. Relist it. Okay, so now after it branches out of the loop, it's going to load the accumulator. See how much of a workhorse that accumulator is? It's really temporary storage for a lot of things. You're just going to take values from one place and put it somewhere else, or take value from one place and have something else act upon it. That is the absolute foundation, fundamental way this microprocessor works. Get used to it. You're going to use it a lot. So after it's done with the loop, it'll load the accumulator with that same value, which represents a shift clear key press, and then outputs it to character out kernel call. Alright, so I'll run this again. It compiled cleanly, SYS 49152, and there it is, holding on us to hit a key press. Hit the key press, clears the screen, and we're done. That's a lot neater, except we repeated code. We repeated lines 33 and 36 at lines 120 and 130, and we don't necessarily need to do that. If we find that we're creating reusable loops of code, then let's make it a reusable loop of code. So bear with me on this. I'm going to start line 1000. Okay. And I'm going to give this a label. I'm going to call it CLRSEN. Okay, oh, SEN. Let's try the N this time. And we'll set this at, equals program counter here. Why did I use line 1000? Just so it looks separate from the rest of it. It could be line 131 and it would still work. It just happens to be the next line in the sequence. So I'm setting a label here. And then in this section of code, I'm going to put my LDA 147, the immediate mode, the actual value, and then line 1020 JSR FFD2. Then this is going to be called a subroutine, and what I'll do is I'll tell the program to jump to where this subroutine starts, and when it'll execute the program at that point, and then when it comes across an RTS, it'll stop. It'll actually won't stop. It'll jump out of the subroutine and continue on from where it left off. So let me list this here. Okay, so, and this is where the line numbers come in handy to indicate that this is out of place, and it's easy to see that it's out of place. So all I need to do is, wherever I have in code, I'm repeating those two lines. I just need to change, like here, in fact, I'm going to do it down here. We'll list it later and look. I'm just going to do line 33. I'm going to clear line 33 out by hitting line 33, hit enter. I'm going to clear line 36 out, hit enter. You'll see that, this is from basic, so you see down there they're going for basic. So instead, I'm going to do line 35, JSR. Bear with me here. Yes, spring's on the way, and so are the flies and the butterflies, and the dogs bark at those. So anyway, so we're going to jump to the subroutine called clear screen, our own homemade subroutine. Again, why am I hitting the R instead of the N? So when I list this, after it sets things up, the first thing it'll do is it'll jump to the subroutine down here, clear the screen, and the RTS makes it return, and then comes back to what's here at line 40. And so we want to clear the screen again when it's done with this loop. So line 120, and I'm just going to edit it right here. We can do a JSR CLRSCN. And then I'm going to replace line 30 with an RTS, and here's why. When it compiles this, after it compiles this line, it's going to continue and compile this line. Internally, it won't be a line 130 or line 1000 or whatever. It's just going to be the next series of bytes, which represents in this case, the LDA. If I put my subroutine codes down below my main code, if I don't put an RTS in there, it's going to fall through and start executing my main code. Now, I could use this as my advantage here. I can actually take line 130 out, and in this case will work, because after we're done with, I can actually take line 120, 130 out, because after my loop is done, it would just naturally fall through to the same code I want it to execute anyway. It works if you can do it. It's just poor practice. You should really keep control of where you're looping your stuff, because you're going to find if you write bigger and bigger programs, it's going to get harder to manage that. So I'm going to go back up here real quick. Line 120, I'm going to hit enter and enter again, just to make sure those got entered into the system. I'll hit list. And everything looks good here. We're going to jump to our own routine to clear the screen. Load X with 0 to start our loop. Load, save, or load, store, increase X. Loop. Here we're going to start our waiting period while we'll wait for a key press. And then if the key press comes in, we're going to run our clear screen loop again and then stop the program. So I type run here to compile it and hope I don't get any errors. Looks good, and as you can see, it's getting bigger. Now it's from C000 to C01C on hexadecimal. SYS 49152. Crossing fingers again. Okay, we expected that. And then when we hit a key, it does what it did before. But we saved a few bytes of memory just by reusing a couple lines of code. And that's all I'll go over in this video. I didn't realize I spent an hour discussing this. Most of my videos do tend to run long, but I want to make sure my train of thought in instructing you on this goes through and goes well. So thank you for watching this one. I will continue with this in another video.